Welcome to Math with Professor V. In this video, I'll be solving exam 2 that I gave my multivariable calculus class or Calc 3 class this summer 2025. And it covered the second unit in this course, basically functions of several variables, partial derivatives, limits, related rates, finding absolute extrema, Lagrange multipliers, and lots more. If I were you, I would definitely check out all the video lectures covering the topics in this unit that are linked in the description before watching this video, because I'm going to basically be working through the examples and providing minimal explanations. Okay, so first problem asked us to identify at what points are the given functions continuous, and be sure to use correct notation. So we have a theorem that tells us that pretty much every single function you can think of, rational, radical, trig, inverse trig, exponential, logarithmic, and combinations of these functions are continuous on their domain. The only group of functions that doesn't fall into the categories covered by the theorem are piecewise defined functions for the most part. So basically all we need to do here is identify what kind of function we're dealing with, identify its domain, and then by that theorem, this function is continuous on that given set on its domain. So notice here f is a rational function. Its domain would consist of all xy on which this expression here is well defined. So what would make a rational function undefined? If the denominator is 0. So let's see if there are any values that we need to exclude from the domain. So what do I not want to happen? I don't want 2x squared plus x minus 6 to equal 0. This factors into 2x minus 3 times x plus 2. So basically, x cannot be equal to 3/2 or negative 2. So our domain, and here's where you need to be careful, is the set of all ordered pairs xy such that x is not equal to 3/2 or negative 2. Okay, make sure you're in the right dimension, basically. You wouldn't say your domain is all x's because this is a function of two variables. And then you write that vertical line such that, and then you list basically your criteria or your restrictions. Okay, let's look at the next one. G of xy equals the square root of x plus the square root of 1 minus x squared minus y squared. So this is a combination of a couple radical functions, but yes, the theorem applies to radical functions. They're continuous on their domain. Here we have square root of x, so that tells me x has to be greater than or equal to 0. And then the radicand, or the expression under the second radical, is 1 minus x squared minus y squared. So that adds the condition that 1 minus x squared minus y squared also has to be greater than or equal to 0. Another way of writing that is that x squared plus y squared has to be less than or equal to 1. And I need to basically list both these conditions, okay, as in my domain. So I would say the domain for G is all xy such that x is greater than or equal to 0, and x squared plus y squared is less than or equal to 1. And G is continuous on its domain. All right, very good. Moving on, f of x, y, z. So now notice the domain contains x, y, and z. So now we're in 3 space. F equals arcsine of x squared plus y squared plus z squared. So think back, we know that the domain for arcsine of x, or sine inverse of x, is between -1 and 1 inclusive. So what that means is that x squared plus y squared plus z squared has to be between 1 and -1. Now, this expression here is the sum of squares, right? So there's no way that it's ever going to be negative. So it's kind of redundant. If you just want to put x squared plus y squared plus z squared is less than or equal to 1, the greater than or equal to -1 part is automatically handled. If that makes you nervous, I suppose you don't have to do that, but let's be crisp and precise. Okay, so this is an inverse trig function. And we know that, again, it's continuous on its domain. And the domain is right here. Boom. Make sure that you specify all ordered triples, x, y, z. Okay, lastly, f of x, y, z equals e to the x over e raised to the y plus z. So this is like a combo, right, of exponential functions, and we have them divided by each other. So again, like think back to when you're dealing with a rational function, you just want to make sure the denominator is not 0. So we don't want this to equal 0, but that never happens anyways, right? Not possible, or basically it's not possible for it to equal 0. Let me put it that way. So we have no restrictions on the domain. So you could say the domain is all of R3. You wouldn't say all real numbers, that you're in the wrong dimension. Your input is ordered triples. Another way, if you want to put it in set builder, I don't know why. I don't like writing more than I have to if I don't need to. X is any real number. Y is any real number. Z is any real number. You have a few more options, but let's be succinct, right? Yes. Very good. Okay, so that was the first question. Next, we're dealing with limits, probably the most difficult topic for most students in this unit, in this course, or in calculus in general. Students really struggle with limits. I get it. They're more conceptual, and you don't have like a set protocol. It's not like taking a derivative. Here are the rules. You have to stop and think. It can be scary. Okay, find the limit or show it does not exist. So we're finding the limit as xy approaches 0, 0, and they're just like letting you know, hey, don't worry, x does not equal y. That way you don't have to worry about the denominator being undefined, okay? So always try direct substitution, meaning just try to plug in where x and y are going into the expression. See if you get a number, because if you do, then you're done. That's the limit. But no, we get 0 over 0, which is no good. Now you can't apply L'Hopital's rule for functions of several variables, so we have to try something else. Your options are, when evaluating limits, if you're trying to show that it exists and find like an actual value, you direct sub, so you just plug in, or you can go polar, and then sometimes you can use L'Hopital's rule. You can factor or rewrite it, like if you multiply by a conjugate, etc. You could do delta epsilon proof to prove that the limit exists, or you could do the squeeze theorem. That's pretty much it. To show a limit does not exist, that's when you check multiple paths and you show that the limits are not equal. Okay, so that's your strategy. Now, right now, see how the directions were? Ugh, I was mean. I didn't give them a hint which one it was going to be. So direct sub didn't work. I'm not excited to go polar because I don't see like anything squared where I feel like it would be helpful. Let's try factoring and rewriting. See how there's 4 terms in the numerator? We can actually factor by grouping. So this is the limit as xy goes to 0, 0. I'm going to take out the common factor for these 2 terms, which is just a 2. Do you see that? Oh, good. Rad y minus rad x plus, think of this x, it's rad x times rad x. So I'm going to take a rad x out from the next 2 terms, and then I have rad y minus rad x. So slick, right? Good. So rad y minus rad x cancels out. And then now I'm left with the limit as xy approaches 0, 0 of 2 plus rad x. That's it. And then now I can use direct substitution. That's 2 plus square root of 0, which is 2. Beautiful. Okay, that one's done. Let's look at the next example. So we have here the limit as xy approaches 0, 0 of xy squared cosine y over x squared plus y to the 4th. So if we try direct substitution, we'll get 0 over 0. We can try going polar. I'm not optimistic. Let's talk about that later. Factoring and rewriting, no. Delta epsilon, I'd rather not, and I made it optional anyways. We could try squeeze theorem, but if you do, you will fail. So, because I know how this problem works, I'm going to try multiple paths and actually show that the limit doesn't exist. But honestly, like when you're first learning this, you're just going to have to take different routes and fail at it and then say, oh no, let me try something else. Okay. I just have to be honest with you guys. So I'm going to try to show two different paths where I get different values and then I can say the limit doesn't exist. So let me go along x equals 0, the y-axis. So that means I'm going to take the limit now as 0y approaches 0, 0. And then if I substitute in 0 for x, I'd get 0 in the numerator and then 0 plus y to the 4th in the denominator. Now this part's always confusing for students. In the next step, you're not plugging in y going to 0 because you'd have an indeterminate form. You're ignoring this and you're just simplifying this expression here. 0 over y to the 4th is 0. That's the only thing you're looking at. Not all this out here. Oh, and then as y approaches 0, the limit of a constant is just going to stay 0. Okay, so now my goal is, can I get a limit that's not equal to 0 if I take some other path? And kind of a hint that I have is, see how we have y to the 4th? I'd love it if this was y to the 4th. So I'm going to go along the path x equals y squared. Okay, so here we go. Let's look at the limit as y squared y approaches 0, 0. And then I'm going to replace all the x's with y squared. So then you'd have y squared, cosine y squared squared, that's y to the 4th plus y to the 4th, right? Okay, then that's going to be the limit as y squared y approaches 0, 0. This is y to the 4th cosine y over 2y to the 4th. Things are going to work out great for us. So then this is the limit as y squared y approaches 0, 0 of cosine y over 2, which is going to be cosine of 0, which is 1 over 2. And notice these are not equal, which means the limit as xy approaches 0, 0 of xy squared cosine y over x squared plus y to the 4th does not exist. Now, I have a very important question for you. Are you ready? If this had equaled 0, what would I be able to conclude? Are you ready? What did you say? Did you say nothing? Because that's what you should have said. Remember, when we are in 3 space, it's different than when you're in the 2D plane, when you're in Calc 1. In Calc 1, when you have a limit, the only way to approach some point is from the left or from the right. So if you check both of those sides and the limit of the function doesn't come out to be the same, then you could say the limit doesn't exist. When we are in 3 space or higher, there's infinitely many paths on which you can approach a point. Here's just 2 of them. I already got that they weren't the same. But if they were, there's infinitely many more. I will not be able to live long enough to test all of them. So testing paths is never the way to show a limit exists. Testing different paths is only used to show the limit doesn't exist because you get 2 different values, okay? And so just because you get 0 twice doesn't mean you have any helpful information, okay? It's only helpful when you get 2 different values, then you can conclude the limit doesn't exist. So you only test paths to show a limit doesn't exist. Notice I only put it here. If you do want to show the limit exists, we have all these other things we can do. Direct sub, go polar, factor, squeeze theorem, delta epsilon. Okay, so keep that straight. You're only testing paths if you already kind of suspect it doesn't exist. Okay, let's look at this guy. You see all those x squareds and y squareds? To me, it's screaming go polar. That's what it's telling me. Professor V, we need to go polar. Okay, so in that case, I'm going to rewrite this as the limit as r approaches 0 from the right, that's very important, this is going to be e to the negative r squared over r squared. Very good. Okay, so let's see what's going on. As r approaches 0 from the right, e to the negative r squared, that's approaching 1. And then the denominator is approaching 0 through positive values. So hopefully you remember from Calc 1, when you have a non-zero constant, that's what the numerator is approaching, and then the denominator is approaching 0, this whole expression is getting arbitrarily large. Arbitrarily large in the positive direction, since the numerator is approaching a positive constant, and in this case, my denominator is positive. So then we just say this limit is positive infinity. Technically, we would also say, the limit doesn't exist because it doesn't exist as a finite number, but we like to specify in which way it doesn't exist. And so then we would specify, it approaches positive infinity. Okay, no, you don't use L'Hopital's rule on this limit because L'Hopital's rule is only used when you have indeterminate forms of the type 0 over 0 or infinity over infinity. That's the only time you can use L'Hopital's rule, okay? Otherwise, it won't give you the right answer. Or it might by accident, but you shouldn't do it. You shouldn't do it. Okay, moving on. The most stressful part of the exam has now finished. Write a chain rule formula for the following derivative. We need del W, del T, when W is a function of x, y, z, x is a function of r and s, y is a function of t, and z is a function of r, s, and t. So I'm going to make a tree diagram. So W is a function of x, y, and z. X is a function of r and s. Y is just a function of t, and z is a function of r, s, t. And we want del W, del t. So W starts up here. Then at the very bottom, I see two branches that end with t. So to find the appropriate chain rule formula, you just start at W, top of the tree, and then follow the branches down. You multiply as you go down the branches, and then you add when you go one branch to another. Now let's see what's going on here. So this would be a partial derivative since W is a function of more than one variable. So this would be del W, del Y, and this would be del W, del Z. But right here, this is just regular derivative, not a partial, because Y is just a function of one variable. And then this would be a partial, del Z, del T, since Z is a function of more than one variable. So now we're ready to put it together. It would be del W, del T equals del W, del Y times dy, dt. And you do have to have some self-control about you to make those del's look different from your d's. Plus the next branch, del W, del Z times del Z, del T. Okay? And if this was like, woo, over your head, then that means go back, watch my video lecture on the chain rule. It's linked in the description. Okay, another chain rule problem. Evaluate del Z, del V at uv equals 1, 4 for the function z equals xy squared minus ln of x equals e to the u plus v, y equals uv, and you must include an appropriate chain rule formula as part of your solution. So basically, I want this as well. Okay, let's make another tree. So z is a function of x and y. And then x is a function of u and v. Oh, and so is y. Right? Okay, so let's write out the chain rule formula for del z, del v. Here's z, here's the v's. We got to go down this way and this way. Those are all going to be partials. So the formula is del z, del v equals del z, del x times, you always multiply as you go down the branch, del x, del v plus del z, del y times del y, del v. Now it's up to you. If you want, you can just find all those derivatives off to the side ahead of time. So let's do del z, del x. That's going to be y squared minus 1 over x. Del z, del y, x. No, 2xy. Excuse me, I got carried away. 2xy. Okay. And then del x del v e to the u plus v, and then del y del v, so treating u as a constant, derivative's just u. And then I have to actually evaluate these at the given point. So u and v are 1 and 4. So if u is 1 and v is 4, that means x is e to the 5th and y equals 4. Okay. So then this would become 16 minus 1 over e to the 5th. This would be 2 e to the 5th times 4, so 8 e to the 5th. This would be e to the 5th, and this is just 1. Okay, let's put it all together now. So del z del x, 16 minus 1 over e to the 5th, del x del v, x to the 5th, plus del z del y, 8 e to the 5th, del y del v, 1. Okay, this just distributed through, and then we should be able to clean up and be done. 16 e to the 5th minus 1 plus 8 e to the 5th, so 24 e to the 5th minus 1. Boom. Okay, straightforward. Next one, use implicit differentiation to find the specified derivative at the given point. So find del y del x at the point 154 for 3x squared plus 7 ln xz minus 6yz squared minus 3e to the z equals 0. So I'm going to use the shortcut formula since I'm in multivariable calculus now. And let me rewrite this and call this my function of x, y, and z. You see? So this is 3x squared plus 7 ln xz minus 6yz squared minus 3e to the z. And remember, if we want to find del y del x, that's the opposite of the partial of capital F with respect to x over partial of capital F with respect to y. So here we go. Let's try this. Out. Negative partial with respect to x. So treating y and z as constants, what's the derivative going to be? So this would be 6x plus, okay, 7 times ln of xz, that would be 1 over xz, but then z is a constant, so by the chain rule, I'd have to multiply by another z, and then the derivative of everything else would be 0 because there's no x's in it, so those are all constants as far as we're concerned. And then partial with respect to y, that would be 0 because that's a constant, 0, negative 6z squared, 0. That's it. Okay, cool. So these cancel out. This z is now gone. So we just have 6x plus 7 over x over 6z squared. Now, you could multiply through by x to clean it up, but I'm like, hey, they're asking me to plug in a point. Let me just do that now. Like, why simplify anymore? 6 plus 7 over 1. 7 over 6 times 4 squared. 6 times 16 is 96. So this is 13 over 96. Okay, fun. Yes, did you enjoy that one? Good, they did too. Almost everyone got it right. Okay, related rates problem. They happen to be much easier in multivariable calculus than Calc 1. Go figure. So the radius and height of a cylinder are changing with time. At the instant in question, I don't know why that makes me giggle. That sounds so like heightening the drama. Okay, at the instant in question, R is 3 centimeters, H is 7 centimeters, dr dt is 0.01 centimeters per second, dh dt is negative 0.03 centimeters per second. At what rate is, here's the clincher, the cylinder's volume changing at that instant? You must include an appropriate chain rule formula as part of your solution. Oh, wow. Okay, here we go. So notice volume is a function of several variables. radius and height. And both of these are changing with time. So what shape are we dealing with? It's just a cylinder. So we know volume of a cylinder is area of base times height, area is a circle, times the height. So V is a function of R and H, and both of these are changing with time. And then look at what I highlighted in green. At what rate is the cylinder's volume changing? So what they want is del V del T. No. They want dV dt. Why isn't it a partial derivative? Because R and H are both functions of only one variable. Yes. Okay, so what's the appropriate chain rule formula? dV dt would equal del V del R times, this is not a partial, dr dt, plus del V del H times dH dt. You got it? Okay, good. So what's del V del R? Treating H as a constant, the derivative would be 2 pi RH. Then we have dr dt plus del V del H would be pi R squared. And then we have dH dt. All right, and then they gave me all the info I need to just plug it in and be on my merry little way. So this is 2 pi, R is 3, H is 7, dr dt is 0.01 plus pi R squared, and then dH dt. And we'll just throw the units back on at the end. So then we have dV dt equals pi times 2 times 21 times 0.01. So that's 0.42 minus 9 times 0.03. So that's 0.27. So that's 0.15 pi. And then if it's dV dt, you need units for volume in the numerator, units for time in the denominator. Boom. That's the same as 3 pi over 20 if you don't want to leave it as a decimal. But like, to me, when they start with decimals, that's your clue. You can use them too. If they didn't use decimals in the beginning though, I definitely would never have the gall to switch to decimals myself. Heavens no. Okay, we're halfway through almost. Find the derivative of the function at P naught in the direction of U. So what we need is a directional derivative, and hopefully you remember how to find that. So you take the gradient of your function and then you send it in the direction of U, but U has to be a unit vector. And even though they called it U, which usually we use for unit vectors, this one is not a unit vector. So rude. Okay, it's fine. We can deal. So first let's find the gradient of f. So remember that's partial with respect to x, then y, then z. So partial with respect to x is going to be negative 6y cubed z squared, negative 18x y squared z squared, and negative 12x y cubed z. Okay, then I have to basically like evaluate this derivative in the direction of my unit vector. So we're going to take u, divide by its magnitude, and dot it with this gradient at that point, at the point P naught. So what I want is the directional derivative in the direction of u of f evaluated at P naught. So I'm going to have to take my gradient that I just had, evaluate it at P naught, and then I'm going to dot it with 1 over magnitude of u. What's that going to be? Rad 4 plus 1 plus 4, and then just keep u over here, okay? So this is where it gets disgusting. So it's basically negative 6 times 12 cubes times 6 squared, negative 18 times negative 6 times 144 times 36, negative 12 times negative 6 times 12 cubed times 6, and then dot this with, well, the 1/3 I could do, why am I saying 1/3? Because this ends up being 1 over rad 9, right? So you could just pull that out front and then just dot the two vectors here, negative 2, 1, negative 2. And I'm pleased to say pretty much everybody got it right. You should get negative 62,208. My apologies for the ugly numbers. But sometimes it happens, you know? You don't get to choose your fate. You don't get to choose what sort of numbers. Ooh, I'm awake. That's my alarm. What sort of numbers your instructor puts on the exam. So that's that. Also, I did get up at 5 to record this video because I just have a packed day and someone was asking for it. So here you go. Okay, I have to leave in like 2 hours for hot yoga. Let's move on. Find the derivative of the function f of xy equals tan inverse of y over x at the point -6, 6 in the direction in which the function increases most rapidly. That's always in the direction of the gradient. And then notice they didn't ask for the direction though. They asked for you to find the derivative. So your brain needs to translate this question and go, they want the magnitude of the gradient. Half the time, interpreting the directions in math requires you to take the vocab and basically translate it. It's like learning a new language, okay? So here we go. We got to get the gradient of f. Okay. So partial derivative with respect to x. So derivative of tan inverse something is 1 over 1 plus the something squared. And then by the chain rule, okay, I'm holding y constant. I have to take the derivative of y over x with respect to x. Maybe it's helpful to think of it as yx to the negative first. Then the derivative is negative yx to the negative second, which is the same as negative y over x squared. We'll clean this up in a moment. Okay, and then same thing, but we're doing derivative with respect to y. So it starts off the same, 1 over 1 plus y over x squared, but then derivative with respect to y of y over x is just 1 over x this time. Are you with me? Okay. So in the numerator here, let's clean up negative y over. This is cute because it's going to distribute. That'll give me x squared, and then that's just going to give me y squared. Ooh, we love it. And then here, so this is 1 over x plus y squared. It's not making it better, is it? Oh no. Over x squared, and then an x will cancel. So let us come through, multiply by another x, because we don't want that expression to have another fraction in its denominator. So negative y over x squared plus y squared. And then this is going to be x over, oh, this is cute, x squared plus y squared. Look at that. Love it. Okay, perfect. So what do I need to do now? You know what? All I found was the gradient, not the magnitude. We will find the magnitude in a minute, but that's what they want. They want the magnitude of the gradient. Okay, that's precise. So now let's evaluate this at, what's the point? -6, 6. So gradient of f at -6, 6. Okay, be careful. Keep your wits about you. It's going to be -6 over 6 squared plus 6 squared. And then x, same thing. Oh, okay. So that's -6 over 72, right? -1/12. -1/12. So then I need the magnitude. I'm going to teach you a trick. You ready? You're going to like this trick. So when you find the magnitude of a vector, you can take this constant out, okay? That way you don't have to square it and make it all big and ugly. And it's literally just absolute value of that constant times the magnitude of the vector that's left over. Oh yeah. So this is 1/12 times this. Aren't you already more relaxed? They're like, oh my God, I just have to square -1 instead of 1/12. I know, you're welcome. So then this is rad 2 over 12. Perfect. Okay. If the directions had been different, if instead of saying find the derivative, it said find the direction in which the derivative increases most rapidly, then you would just give the gradient vector. So if it says direction, they want a vector. If they say derivative, then they want the magnitude. Okay, let me pay attention. I was being silly earlier. Find the equation for the tangent plane to the surface at the point -1, -1, -1. Again, we're going to use the gradient. I have to rewrite this though, because it's not a function f of x, y, z. Remember, we need gradient to find the normal vector to the surface. So let me just redefine it. I'll say f of x, y, z. I feel like the negative 4z squared is like, please move me over with the rest. It's so lonely over here on the right side. Ain't nobody over here. Like, your wish is my command. So the gradient of f, relaxing polynomial, not like that last problem with the tan inverse. 2x plus 6yz, everybody else is constant, so their derivative 0. Now partial with respect to y, 6xz plus 2y, and then partial with respect to z, 6xy plus 8z. Beautiful. And then I'm going to evaluate the gradient at -1, -1, -1, and we got 4, 4, -2. Now, we could use this vector as the normal to our surface, but then I know I'm going to have to like reduce my equation at the end and divide through a constant, so I might as well do it now. So instead, for my normal, to write the equation for the tangent plane, I'm going to use 2, 2, -1. You can't do this when you're asked to find a distance. You can't like scale down a vector. That would scale your distance. But if you're just finding equation of like a line or equation, when you're finding an equation of a plane, you can totally scale down your vectors. Okay, here's the point. Hopefully you didn't forget how to write equation of a plane. 2 times x minus -1 plus 2 times, you're basically dotting, remember? Y plus 1 minus 1 times z plus 1 equals 0. So then we get 2x plus 2y minus z is -3. Okay, perfect. Perfect. Ooh, this is a good one. Write parametric equations for the tangent line to the curve of intersection of the surfaces z equals 3x squared plus 10y squared and z equals x plus y plus 11 at the point 1, 1, 13. So this is a paraboloid, this is a plane. So hopefully you can imagine, like, I'm not going to draw it in any sensical way. Here's a paraboloid, and then there's a plane, okay, and they intersect, and there's some curve of their intersection, you know? And at this point, I feel like I drew that intersection really bad, but okay. Say at this point, 1, 1, 13, they want the equation to the tangent line to this curve. So the tangent line, here's how you have to think about it. The tangent line, I need a direction vector. Direction vector for tangent line. Well, the direction vector for the tangent line is perpendicular to the normal to each of the surfaces at that point. So if I have the normal to the paraboloid, boop, it's going that way. If I have the normal to the plane coming out this way, the tangent line is perpendicular to each of their normals. So what I need to do is find the normal vector to each surface and then cross them to get the direction vector v. Does that make sense? Okay, good. So I'm going to call f of xyz the paraboloid. So it'll be 3x squared plus 10y squared minus z. And then I'm going to call g of xyz the plane. So I'm going to redefine it as x plus y plus 11 minus z. So the normal to each of these surfaces is going to be given by their gradient. So the gradient of f would be 6x, 20y, -1. And the gradient of g, ooh, it's lovely, 1, 1, -1. Now I need to evaluate these at the point 1, 1, 13. So the gradient of f would be 6, 20, -1. Gradient of g, 1, 1, -1. And then now let's cross them. Just do it in my head. So then this is going to be -19, 5, -14. I did it ahead of time. I'm not that lightning fast. I'm pretty fast, but I'm not that fast. Okay, So basically there's the direction vector for our line. And then I'm going to use this point that was given, 1, 1, 13. And how did they want the equations? Parametric. Hallelujah. So x equals 1 minus 19t, y equals 1 plus 5t, and z equals 13 minus 14t. And we're done. I like to put that little bracket. They go together. Okay, perfect. Find the linearization of the function at the given point. So let's just go ahead, put it all together. Hopefully you remember your linearization formula. L of x, y, z equals, I'll call this point ABC. How about that? So it's equal to f of a, b, c plus partial with respect to x times x minus a plus partial with respect to y times y minus b plus partial with respect to z times z minus c. So let's go get those partials. Yes, let's do it. Oh, it's ln of some stuff. That's not so bad. So partial with respect to x is going to be 1 over everything that's inside those parentheses. And then by the chain rule, we're taking derivative with respect to x. So I got to multiply by -6. And then let me evaluate it at the point that was given, -1/6, -1/5, -1/7. So this is going to be -6 over, oh, do you see that? I hope so. It's going to be +1 plus 1 plus 1. So this is -6 divided by 3, so -2. Similarly, partial with respect to y is -5/3, and then partial with respect to z, evaluated at the point, is -7/3. And then f at the point, -1/6, -1/5, -1/7, is natural log of 3. So then we're ready to put it together. So my linearization, which is always a function of x, y, and z, is equal to ln of 3 minus 2 times x plus 1/6 minus 5/3 times y plus 1/5 minus 7/3 times z plus 1/7. And then let's clean this up a wee bit. So L of x, y, z is ln of 3 minus 2x minus 1/3 minus 5/3 y minus 1/3 minus 7/3 z minus 1/3. Ooh, so I can combine all of those. Let me write it as -2x minus 5/3 y minus 7/3 z plus ln of 3 minus 1. If you want to keep the constant first so that you have the positive ln 3, I could understand why you would want to do that. We'll allow it. Okay, next problem. Find all the local maxima, local minima, and saddle points of the function. You must write your answer in the form of a neatly organized table summarizing your results so it doesn't turn into Hot Mess Express. Okay, so let's go get all our critical points and then put them in the table. So what you want to do is find where both partial with respect to x and partial with respect to y are equal to 0 simultaneously. So partial with respect to x, that's 4x cubed minus 4x. Let me set that to 0. So then we got, let me factor, 4x times x squared minus 1 is 0. So then x can either be 0 or plus or minus 1. And then partial with respect to y would be 3y squared minus 3. Let's set that to 0. So then y is plus or minus 1. So these solutions arose independently of one another. So we're just going to make every possible pairing. Since we have 3 values for x and 2 values for y, 3 times 2, we should have 6 possible critical points. While we're at it, let's get all our second partials. So second partial with respect to x is 12x squared minus 4. Second partial with respect to y, 6y, and then the mixy is 0. Okay, we have 6 critical points. Then here's how you should lay the table out. I shown the lecture. Second partial with respect to x, second partial with respect to y, the mix, d, and then classify the point. Then this way it just sets it up so you can apply the d-test very easily. Okay, let's see if this is going to be long enough. Let me list all the points. So 0, 1, 0, negative 1, 1, 1, 1, negative 1. And then lastly, negative 1, 1, negative 1, negative 1. Perfect. Let me write what each of the partials are. Then we don't have to be on a scavenger hunt. We can just be relaxed. Set yourself up for success. Like, do the little things that make a difference so that when you're computing, it's as easy as possible. Because, like, I feel that the majority of the time my students mess up. They're just making silly mistakes. So you want to eliminate that. Okay, here we go. Negative 4, negative 4, 8 the rest of the way. 6, negative 6, 6, negative 6, 6, negative 6, 0, 0, 0, 0, 0, 0. D is fxx times fyy minus fxy squared. I don't care what number it is, I just care about the sign. Minus, plus, plus, minus, plus, minus. Whenever D is negative, that's a saddle point. When D is positive, then we got to look at second partial with respect to x and see the sign. So here it's positive, but this was negative, which means this is a local max. D is positive, but this is positive, so that's a local min. D is positive. Oh, I should keep my color coding. Positive, positive, local max. No, local min. I lost my mind. You can graph it to check too on Desmos 3D. Why not? You should. Okay. Oh, there's more. There's more to the exam. But you know what? I'm tired and I need to go to yoga. There's questions 9 and 10, and then there's 2 extra credits. So I'll do them in a part 2. Unless you guys are over it. So comment below if you want to see part 2, see me finish the exam. And I did give them